In this session, I'll discuss the raster components of NHD Plus version 2. A raster, as I'm sure you all know, is a matrix of cells or pixels organized in rows and columns and represented by a value. For example, the NHD Plus catchments are created where the value of the raster identifies the catchment. That's the grid code that you've heard mentioned before. There are other secondary rasters that are created in the catchment development process that are useful for other purposes. We include these secondary rasters in the NHD Plus v2 data set. I got a problem here. Oh boy. Oh, okay, there we go. Okay, the NHD Plus training, yeah, here we go. All right. In this webinar or series, we'll cover the rasters that are included in the NHD Plus data suite. We'll also cover how these components are used to develop the catchments, as well as some vector data that's also used to develop the catchments. And finally, we'll discuss, some other possible uses of these other rasters. Okay, so after a brief introduction into the raster components, we'll discuss which ones are used in developing the catchments. It's the CAT grid, the Hydram, the flow direction grid, and for each we'll cover how the component was used to develop and offer examples of how they can be used as well. We then describe the additional raster components and provide examples of their use, the flow accumulation grid, the FDR null grid, and the filled area grid. This is a simplified schematic diagram that shows the components of NHD Plus version 2 data suite relative to the catchments. In the data suite, CAT is the catchment grid, the product of the raster processing. The featured class catchment is the vectorized version of CAT. Both the CAT and catchment are distributed by the entire vector processing unit, or VPU, which is typically a hydrologic region, a 2-digit hydrologic unit. The 6 items within the oval represent raster components that are distributed as grids. All of these are distributed by the raster processing unit, the RPU, which can be either the same size as the vector processing unit or significantly smaller. There's a software limitation on how big an area can be processed together at once. The grids Hydram, FDR, and CAT seed shown here are used in the creation of CAT, the grid of catchments. The first of the 3 grids is Hydram. This is a hydrologically conditioned digital elevation model that we'll discuss further in this session, as well as the burn components, which are used to create the Hydram. The Hydram is used to create a flow direction grid, the FDR, which is then used in conjunction with CAT seed to create the RPU-wide grid of catchments. These grids of catchments for each RPU are not distributed by the RPU, but as you've heard, are a single CAT for the entire vector processing unit. All processing is done in a map projection that is appropriate for grids or raster processing. For the 48 contiguous United States, this is the Albers projection. The catchment shapefile is generated from the CAT grid, which already has been combined from the RPUs and covers the entire VPU. The catchment shapefile is a multi-part polygon shapefile. In the example shown, if catchment were not created as a multi-part polygon, the rasterization of the CAT grid would have resulted in 5 separate polygons to represent the catchment for the flow line shown in the red. By processing the data as multi-part polygons, these 5 polygons are combined into a single multi-part polygon feature. A catchment within either the cat grid or the catchment shapefile can represent the drainage area to either an NHD flow line or to a sink that is isolated and not associated with a flow line. The Hydram is a hydrologically conditioned elevation model. For this elevation model, prior to hydrologically conditioning it, we start with a national elevation data set, 1 arc-second NED, referred to in NHD Plus data set as the NED snapshot. The NED snapshot is then modified or hydrologically conditioned by using the burn components. The burn components will be covered a little bit later here. 2 examples of the burn components that are used to modify the NED snapshot in order to create the Hydram are the burn line event, a rendering of the NHD flow lines, and the watershed divides called walls. The divides or walls come from the 12-digit hydrologic unit boundary, WBD boundary set. This figure and the one on the next slide illustrate how the 2 burn components, burn line event and wall, are used to modify the digital elevation model in order to create the Hydram. The sole purpose of creating the Hydram is to have a surface from which the flow direction grid is created, which points downward from the ridges or the walls across the land surface to the streams. For this purpose, the locations of the rivers are represented by the burn line event are burnt into the Hydram. The surface can then be used to create the FDR and catchments. The catchments are identified by unique colors, each represented a drainage to a specific flow line. Okay, the flow direction grid, or FDR, is developed based on the hydrologically conditioned elevation model. And if you're not familiar with the flow direction grid, it's essentially made up of pointers or integers that indicate for any cell the direction downward to the lowest of its neighbors. This figure illustrates how the FDR works. The cell, we're looking at the center cell. If the lowest downward direction is to the east, it's populated with a 1. If the lowest downward neighboring cell is to the south, or 2, it's to the southeast, 4, it's to the south, and so on. And you'll note that the numbers are going up by a base 2 number ordering system. If it's populated with a 0, this indicates that the location is a sink. This is where the surface water exits the system and enters the ground. This figure illustrates, along with the next slide, how the cells of the flow direction grid point downwards from the ridge to the river. The cyan colored lines shown on the slide represent the streams. This is the same figure with the same cyan colored lines. However, the direction pointing down to the stream is indicated with the different colors. The green cells are populated with a value of 2, indicating that the flow is northwest to southeast, again pointing towards the river. And the dark blue cells in this illustration indicate a flow direction to the northeast, again towards the river. There are other uses of the flow direction grid besides creating catchments for streams or to sinks. Drainage areas can be delineated from points off the stream network, or drainage areas can be delineated for midpoints along stream reaches for some point of interest, such as a sampling point along a stream. The point of interest may not be right at the downstream end of a flow line, but rather at some point midway up the flow line. This figure and that on the next slide will illustrate these uses. For example, the surface drainage above a point on the land surface, such as a well, or a point along a stream, such as a sampling location, can be determined. In these examples, the delineation area comprises only a portion of the catchment for that flow line. The segments, the stream segment is in blue, the boundary of the catchment to the flow line is in red, and the smaller drainage areas within the flow line catchments are shown in green. The surface drainage above the well, shown in green on the right, is one such example where the FDR can be used to delineate a drainage area. Similarly, the drainage area above a sample site that is not at the downstream end of the NHD flow line can be delineated by use of the flow direction grid. An example of that's shown on the left. There are three other rasters or grids that are part of the NHD plus V2 suite of data. These are the flow accumulation FAC grid, the filled area grid, and the FDR null grid, which are explained in the following slides. The flow accumulation grid is based on the flow direction grid, the FDR. The FAC, the flow accumulation grid, is an integer grid that represents the count of the number of cells draining to each cell within the RPU. The flow accumulation grid values only represent the number of upstream cells that drain to a given cell within that particular RPU. Cells from upstream or adjacent RPU production units are not included in the count. In this example, the flow accumulation FAC grid is shown in red. It represents a pattern or paths of potential smaller streams that may be tributary to the NHD stream network, but are not included in the network. The 100,000 scale NHD flow lines in this illustration are shown here in blue. The FAC grid cells with more than 500 uphill cells are identified in red. These red lines, or raster cells, indicate potential paths of smaller stream cells, and they are underneath the blue lines as well as where they're covered up by where they're not covered up by the blue lines show where the potential smaller paths and smaller streams may exist. The FDR null grid is just like the FDR grid, except that the stream cells at flow lines are replaced with no data. It too is based on the hydrologically conditioned digital elevation model. The modified flow direction grid is useful in determining how far down a hill it is from any point within a catchment to the flow line. This figure illustrates how that FDR null grid can be used in conjunction with the flow length command to measure distances from each cell within a catchment down to the flow line, which has been made null. The orange shaded areas used show the results of just such an operation where we identify a 500-meter buffer around the flow lines. Further variations of this can be to replace not only the flow lines with no data, but also the networked water bodies as well. In that case, you'd be able to delineate a similar buffer zone around the water bodies.
So that's a buffer based on flow distance instead of utility distance? Right?
Flow distance.
Yeah, maybe you can repeat that.
Okay, it's the flow length command. Yeah. It's the distance down. It's not necessarily a straight line down to that. It's but takes the path of the flow downhill to the flow line.
Repeat the question, please.
Okay. Curtis just wanted me to point out that these buffer zones are not just a Euclidean distance, which you could do with other techniques, but it's actually following the path downhill that the grid is pointing. So it can be a circuitous path, not a straight line, not just a straight line. The last grid that we distributed is the filled area grid, and it's an integer grid. And it identifies the cells from which our hydrologically conditioned DEM are filled. After burning the streams in, the last step in creating the hydrodem is to run a fill command. And the purpose of this is to fill any small pockets within the hydrodem so that the subsequent flow direction grid always points downward towards the flow lines. Or to an off-network sink. If, however, there's conflicting information basically within the ingredient data sets that go as input into the creation of the hydrodem, you can get larger areas that are filled, for example, the WBD may be in conflict with with our NHT. Okay. So basically, the filled area grid is used as a QA process where we look for these large areas where it's been filled. This slide shows an example where we use the filled area grid. The figure shows a large area. It's pretty much most of the HUC-12 that was filled during the creation of the hydrodem. It's indicative of inconsistency between the NHD, which are the blue lines, and the red line, which is the WBD, and the underlying topography of the NED snapshot. The catchments are shown as catchment boundaries are these thinner red lines. So basically what happened is right up in here, the WBD crossed over, was breached by the NED in a spot where it just wandered too closely. And so what happens is when we do the fill, this was a closed basin. But it's not identified as a closed basin. There are no NHD lines in it, and no sink got placed in it. So it ended up filling until it reached the breach, and this large area got filled up. So that's a QA tool. And that's it for the rasters. Again, additional information is available in the NHD Plus user guide. Any questions? Yes. Yeah, the question is, what is the threshold for the NHD lines? And it's really whatever came off of the 1 to 100,000 scale maps. It's what's represented in that. They created something called a DLG, a digital line graph, which is just the lines from that 1 to 100,000 scale map. And you'll see in a presentation in about an hour how much that can vary. That can vary from one quadrangle to the next.
Oops. Hold on.
Oh. I've got one over there, too.
All right,
I'll get you next.
I'm wondering for, it seems like possibly fill and then weird watershed boundaries would be very common in flat areas, and so in our Central Valley agricultural areas, it's really challenging to do some of these things. Would you say that that's an area where we should really watch out for these kinds of boundary crossings and fill problems, or is there where should we think about it? What kind of landscape?
Yeah, I think that where the topography is more gentle, you're more apt to run into problems because it is harder to define the watershed boundary. It's a major effort that's done nationally that and pretty much manually. And I think the wetland areas, like in the coastal areas, we've had is especially difficult.
Central Valley is pretty tough.
Yeah, my question is like for the cell that is at the top of the watershed, like at the ridge, how to determine which direction does that the flow goes, which side of the watershed, like this side or that side? How to determine that? Not the flow direction. Flow directions from that cell, which direction it goes, like how to determine that?
Can you, yeah, if you...
Yeah, so basically the basin fills up. Right on top of the ridge.
Oh.
We call those the Humpty Dumpty cells.
Yeah, the question really is what happens right on top of the wall that we build, and it basically can go either way, and it's kind of random right along that 30-meter line. Right. You know, so
any direction like when we decide that, so we can just randomly assign that, or how do we decide? Like, is this kind of quite fuzzy area, you know?
The software just did it for you. You don't have to decide, but you just have to recognize the fact that it's only accurate to the 30 meters.
But like when you develop that software, you should have some idea or some assumptions or some hypothesis. You must have already applied that, right? When you kind of like develop that, so what was the hypothesis you applied?
So basically what was done was the boundaries were turned into walls. So the lines that were in the WBD were rasterized. So then they have a width, actually, a one-cell width. And the software just randomly sends the tops of that one-cell wide wall one way or the other. There was no control over that.
Well, it should go to whichever the neighbors is the lower.
Yeah.
So,
right.
But it may not be it may it's not perfect.
Yeah.
But the walls aren't raised to an equal value. They've been added to. I'm sorry, the walls aren't raised to an equal value. They're actually added. The walls are added to the elevation, right?
To the terrain.
So the shape of the divide is actually taken into account in the shape of the topography. But, you realize you are way down at the resolution of the data. So,
right.
And even on the vector side, you go to 30 meters. We're getting zoomed in pretty far. It's time to go to high res, right?
Right. Were there more questions?
Get to continue to use their